In bridging to Yorie, I just want to make a couple remarks, which is we see this enormous diversity in the hardware, say in the retina, but throughout the brain. Incredible diversity, extreme diversity, much more so than we see in our engineering hardware, as Toby pointed out. And we also see lots of stuff that's been considered noise. And these two features of neuroanatomy have been viewed as an annoyance by most theorists. What we're trying to do, and Yorie is going to try to do, is say it's not noise and that diversity is functional. Spikes matter, and all that enormous diversity is extremely functional in creating robust systems level. So Yorie's got her PhD at Caltech a year ago and has just finished her first year at Carnegie Mellon, where she's a new assistant professor. And so she's going to hopefully kind of tie all these themes together. Yorie?
Yeah, Yorie, I stole your Zoom picture to stick it on the slide. I hope you noticed that, and I may steal this picture as well. So yeah, please take over. And I specifically was very excited to hear that Yorie was going to present this, because I've been hearing John mutter about it for the last few years, but I just went completely over my head what he meant by diversity. So really, I'm hoping to get it clear now. Hope that's okay, John. Go ahead, take over the screen.
Now you're really hearing from the expert and not secondhand from me.
Right, right. Who can explain to the newbies? So I need to make you a co-host, right? Is that true?
I think I'm already the co-host.
I think you're already the co-host. So you can just take over the screen sharing and show your stuff. And I hope you appreciate the style here. I hope there's going to be some more feedback control. You're calling East Coast time, right?
Yes, I am in yes.
Okay. Great.
I just shared my screen, but I can't see which screen I shared.
It's fine. I see your title slide.
Okay, perfect.
I can see your title slide and your co-authors.
Sure, great. I think that's the right screen to be shared. Thank you so much for the invitation, Toby and John and Terry. It's my great pleasure to be here talking about the diversity-enabled sweet spot. And the motivation of this talk is that so we observe a remarkable robustness in sensorimotor control. For example, in this video, human can bike in a very bumpy and twisting road, and then creating a similar robustness in autonomous system will be much more difficult compared with how we can learn them. And so this talk.
By the way, Yorie, I have to interrupt you here right away in a typical Telluride style. And this whole mountain biking stuff came directly from Telluride, because if you come to Telluride, you can hop on the gondola with your mountain bike and do these endless loops basically without burning much energy. It takes you up and then it takes you down. In fact, we recorded Silicon Retina video, half-hour run with a backpack laptop of just raw Silicon Retina data on a mountain bike. This is a different trail. I don't think it's Telluride, but all this stuff was from Telluride. So it's an advertisement, yeah.
Right, yeah. I think I randomly find this from online, but I'm glad
I have to send you the Telluride video, yeah.
And so this talk, we essentially ask this question of what are the mechanisms that enable this kind of remarkable robustness? And then we will try to connect this with the extreme diversity observed in our nervous system. So to study what enables robustness, we need to first identify what are the limiting factors for the robustness. And one limiting factor is the hardware of our body, such as the speed and accuracy, nerve signaling, or muscle activation. And when we look into this nerve signaling or muscle activation, both of them will have a stringent speed and accuracy trade-offs. And this trade-off comes from the fact that biological resources is limited. So there are only limited budget to build and maintain these muscles and nerves. But when we use inaccurate or imperfect hardware to implement sensorimotor control, the resulting system is also likely to be slow or inaccurate as well. So in other words, stringent hardware trade-offs can constrain the speed and accuracy of the control system as a whole. But in many cases, these hard limits in components does not directly translate into the performance limits of the whole system. So put it differently, sensorimotor systems are intelligently designed so that the performance limits due to hardware are somewhat deconstrained. And so in the next two slides, I will elaborate more on the contrasting hardware and system speed and accuracy trade-offs. At the hardware level, we can look at some example of nerve fibers. And this plot shows the composition of different type of nerves. And there is an extreme heterogeneity in terms of the size and number of axons. And some types of sensory nerve will have a large number of axons, while other types will have axons that are large in size. But we can see that none of them are both large in size and number. And this is because the brain does not have unlimited resources to build and maintain axons. So having an axon at this corner will just spend too much biological resources to build and maintain. And roughly speaking, large number of axons can transmit more information, and bigger axons can send faster spikes. So assuming a fixed resources, we can translate the number and size trade-offs into the speed and accuracy trade-off in nerve signaling. For example, in spike-based encoding of myelinated axons, we can show that the delay and data rate in signaling is linear under certain assumptions. And the specific form of the speed and accuracy trade-off depends on how information is encoded in the spikes. And we have also derived the speed and accuracy trade-offs when the information is contained in the rate, presence or absence of spike, or spike timing, and other forms. And but regardless of the specific encoding schemes, all of them will have some speed and accuracy trade-offs. And the framework we introduced today does not depend on the specific encoding schemes, and we can work with any hardware speed and accuracy trade-offs. And the one important aspect to note is that at the hardware level, speed and accuracy trade-off are pretty stringent. So speed and accuracy trade-off in nerve signaling take mostly like a linear form across different encoding schemes, although there are some slight bit of difference. And also similarly in muscle actuation, the speed and accuracy trade-off follows different models, but they are also stringent as well. So having nerve here are just too expensive. But when we look into the system level, this kind of stringent trade-off actually vanishes into a much less stringent trade-offs. For example, we can consider how to reach a target of distance d with risk w. And Fitz's law states that the relation between the reaching time and the target risk will satisfy this formula for some constant parameters a and b. And here the reaching time will quantify the speed, and the target risk quantifies the accuracy, because the smaller the target, the more accurate the reaching needs to be. So this formula essentially characterizes the sensorimotor control system speed and accuracy trade-off in reaching tasks. An important observation here is that this formula takes a logarithmic or power law. And because of this power law form, there is a sweet spot at which we can achieve speed and accuracy at the same time. So if this formula is to take something more like a linear form, then this sweet spot will immediately vanish. Please.
Yorie, I have to interrupt you. I've actually measured this Fitts law because we were trying to build a new kind of computer mouse that gave tactile feedback. So I've actually measured this Fitts law, but this Fitts law that you're showing here is really just as consequence of the search principle that you're using. You know, you do a big saccade, then you do a correction, right? So I believe that's where this logarithmic behavior comes from. It's kind of a tree search. Isn't that the real reason? And that's different than this sweet spot. This observation of this Fitts law.
No, Toby, that's not it. You'll see.
Okay, all right, okay.
So we will get to this in the later part of the talk, but typically Fitts law is explained using information theoretic manner in terms of the amount of information required to be able to do the search. And then but certain type of routine task that the control aspect, in terms of the motion will be more of a bottleneck. And then we'll get to that later in the later slides. But thanks for the clarification, Toby. And so next, this Fitts law is just one example of power law. And there are many other power laws that also captures some kind of sensorimotor control and learning behaviors. And then these laws are listed here. And so the above two slides show a contrasting speed and accuracy trade-offs at the component level and at the system level. And human sensorimotor control system can achieve fast and accurate performance using slow or inaccurate hardware. And this motivates us to ask the question of how the hardware limits the stringent speed and accuracy trade-offs in this context can be deconstrained to create a much less stringent system speed and accuracy trade-offs. But these contrasting speed and accuracy trade-offs at the mechanisms to deconstrain hard limits have received little attention in the existing literature. So in this talk, we will present our initial effort in connecting the neurophysiological speed and accuracy trade-offs and the sensorimotor control system level speed and accuracy trade-offs. And then we will model how the neurophysiological speed and accuracy trade-offs will impact the speed and accuracy trade-offs in sensorimotor control. And in doing so, we will introduce a concept called diversity-enabled sweet spot. And in short, this means that effective layered control architectures with appropriate diversity is really critical to achieve fast and accurate performance despite imperfect hardware. And so in the later talk, I will discuss the implications of diversity-enabled sweet spot in effective layered control architectures. And we will also connect this the observed heterogeneous nerve composition with the diversity sweet spots. And the insights about how to achieve robust performance using imperfect hardware will be particularly useful in modern control systems. When we consider modern control system applications, such as the Internet of Things or cyber-physical system, they have fundamentally different design space compared with the conventional control system applications, such as the airplanes. In conventional control applications, we can afford to use the most expensive hardware, and with almost perfect hardware, as long as we have a good controller in each layer, we can naturally achieve fast and accurate system performance. And this can be done without a careful design of layered control architectures. However, in many future control applications like autonomous driving, the use of affordable hardware will be critical for the penetration of large-scale deployment. So for the perspective of having to use imperfect hardware, it is more like these systems are more like human sensorimotor control system rather than the conventional control system applications. And so the human sensorimotor control system and modern control applications are similar in the sense that both need to achieve fast and accurate system performance using cheap or imperfect hardware. And this motivates us to seek for effective layered control architectures that fundamentally improve the performance limits. And more specifically, let's consider the commonality and differences by taking the example of human driving versus autonomous driving. Their commonality are imperfect and heterogeneous components. In human sensorimotor control, different types of nerves and muscles have heterogeneous speed and accuracies. And in autonomous driving, different types of sensors are heterogeneous in its capability. Their differences are that human has much more robust and flexible behaviors. And this is because human exploits heterogeneity using layered architectures so that the hard limits in components doesn't translate into the overall performance. While in contrast, a thoughtless choice of architectures using imperfect hardware can easily allow the hard limits of individual hardware or layer to become the bottleneck of the whole system. And so this contrasting example suggests the potential in understanding what architectures can deconstrain hard limits and use such insights to inspire the design of autonomous driving and other technological systems. And so the talk outline is that we have already described the hardware speed and accuracy trade-offs. Next, we will describe the system trade-offs and then connect the system speed and accuracy trade-off with the hardware one, and then end with the diversity sweet spot and its implications and future work. And so this is our experimental platform. This is a typical one where the subject will be looking at a screen that shows the actual position and the desired position of the trajectory. The goal of the subject is to minimize the errors between the actual position and the desired position. And here the vertical dimension shows the future trajectory. This is equivalent with the fact that when we drive, we can see the future trajectories before we reach them. And we model the error dynamics as follows. That is, the current error is the sum of the previous errors and new disturbances that can potentially come from the changing trajectory or bumps in the road, minus the control action that is acting to minimize the errors. And we consider that human sensorimotor control system, it's trying to minimize this error by first sensing this environment and then compute appropriate control actions, and finally actuate control actions using the muscles. And to model the hardware limits, we assume that this feedback loop have a delay of t, that is the sum of the nerve signaling delay subject to the speed and accuracy trade-off and other internal delays, and minus the potential advanced warning. And we assume that this feedback loop also have a limited data rate to limit the accuracy of the feedback control. And we can show that for any controller with delay of t and rate r, the worst case error in infinity norm it's lower bounded by this formula. And this formula has a very clean interpretation. That is, the first term it's only a function of the delay, and therefore they can be interpreted as the error due to delay. And the second term is only a function of the data rate, and they can be interpreted as the error due to having limited data rate. The last slide considers worst case errors, but similar formula can also be obtained for average error or in a stochastic framework. Here again, the error also splits into two parts. The first part can be considered as the delay error. The second part can be considered as the rate error. And then, like, you know, these are the, so we also developed some new high school level control theory so that we can explain why we observe this delay error and data rate error, to almost everybody, including high school students that help us do the experiment. And if we have time, please ask me in the question. I'll be happy to go over them in detail. But for now, I will skip them. And here we will have a forthcoming control theory paper of the same author targeted to neuroscientists. And then we have also published a control theory paper using simplified control theory. And then John have a Dropbox that contains a lot of materials. And then I'll be also teaching a new control theory courses aimed at broadening the audience of control. And I plan to publicly share the lecture notes in spring 2021. And so let me go back to the talk. And now we have the system speed and accuracy characterization. Next, we want to connect the hardware speed and accuracy trade-offs with the system speed and accuracy trade-offs. And so the hardware speed and accuracy trade-offs is what I showed in the beginning of the talk. And the system speed and accuracy is quantified using the delay errors and the rate error in the previous slides. The system speed and accuracy trade-off will be obtained by plugging in the hardware speed and accuracy trade-off into the delay errors and rate errors. And here, although we are using the hardware speed and accuracy trade-off for spike-based nerve signaling, this can be easily replaced with other form of speed and accuracy trade-off, potentially coming from different type of encoding method. And this plot shows the system performance when we vary the delay and rate subject to the hardware speed and accuracy trade-offs. As the rate increases, the rate error will increase. The rate error will decrease, but the increased rate comes with increased delay due to the hardware speed and accuracy trade-off. So the delay error will increase, and the minimum total error, which is the sum of these two, will be achieved at when the rate error and delay errors are balanced well. And so this insight is this insight is different if we are just to consider the neurophysiological level about the component properties. For example, if we are just considering the component properties such as maximizing the speed or maximizing the rate of information in signaling, we will end up at the two extremes, and there the performance will actually be suboptimal. And then so therefore this suggests that the importance of taking a holistic perspective of both the neurophysiological levels and the sensorimotor control levels.
I had a question.
Please.
This is Andreas. On your diagram here, you're talking about the delay error is in bits and the rate error is on top, which is in what units?
So here the delay error and rate error are all becoming the units in terms of the measurement of the error. So
in bits.
Not anymore in bits.
What are they? Because you're talking about delay error, and delay is not really equivalent. What is the units?
So the R is the bits, and the units of the delay is the time. You can.
What is R? R is the rate.
Yes, R is the data rate. It's in bits, and
bits per second.
The T have a unit of time, so you can consider it as second or thousand.
Okay. Yes. So.
But when we consider the total error, if you go back here, it's essentially the size of this error.
Mean square. Okay.
And then, like, you know, the control theory part have already converted the delay error, the delay and rate into a unit that talks about the, like, you know, the size of the size of the space.
Okay, so I think I asked the wrong question. That was really not a very good way to ask that question. Rate has units of bits per second.
That's right.
Where is your seconds there?
Second, it's the sampling rate of the control.
I see. Oh, you're assuming a fixed sampling rate implicit, and so then there is a bits per second rate. Okay, thank you.
Thanks for the
I think he's asking why how the units can be the same between the blue and the red there. You know, maybe it's just an elementary question, right, for the beginner.
Yes.
How can there must be some factor in front of those that makes the units equitable.
Right. So we assume there's a fixed sampling rate, and this sampling rate have the bits per unit time. So this sampling rate goes to the unit time for delay and R, and then makes them uniform, and use control theory to convert these quantities into the actual size of the errors in control.
Okay, we are mostly dealing with continuous time, so I mean there seem to be this is sample data systems. Okay, thank you.
Right, and similar result can also be considered for continuous time. There is an equivalent result like this.
Okay, thank you.
And so we have so Quine, our collaborators also helped verify our theory. And here the right side is the theoretical prediction, and the left hand side is the experimental result obtained by Quine. And next, we will use these results.
Wait, could you just comment on that? I mean, they look similar. You know, it's real data, right? Yes, this is verification. Yeah, so it looks similar.
Right. And so what we did is that we considered a system where we externally add delays, and this creates the delay error. And we also considered a system where we externally added data rate limits, and then created and then measures the error of the rate. And then finally, we considered a system that have added delay and data rate to the feedback externally, and then we compare these three errors.
Okay.
This is humans on the driving game. So there's 3 experiments here. It's just to see, is it plausible that humans can do this? And it is plausible.
Plausible, yeah. It doesn't have quite the same, clear minimum, right? Looks quite flat.
Right.
Yeah, the point this was trying to make was we've got 2 tasks, the bumps and the trail, and an optimal controller, they add up. But most things humans do don't add up. If we text and drive, we crash. So it's on its face implausible that humans can even do this. And this is just, is it plausible that the total error is the sum of the two errors? In a combined task, do we multiplex well? And in fact, we do. So for this task, we're really good at it. And that's the point of the experiment.
Thank you.
And so next, I will use these insights to study what are effective layered architectures, and then connect this with the concept of diversity-enabled sweet spot. So let's take the example of a visual system. Visual system have two separate it has many feedback loops. That there are two major feedback loops. There is a fast feed-forward VOR loop that compensates for head motion, and a slower visual feedback loop through the visual cortex that helps track moving objects. And an important distinction of these two loops from the control perspective is the level of advanced warning in these two loops. And because changes in the visual environment are highly predictable, the visual loop can plan eye movement in advance. And but the VOR loop can only react after the head moves. And then, so in the next slides, we will look into the implication that the visual system has much more advanced warning than the VOR loop. This plot shows the value of the internal delays or advanced warnings on the x-axis and the system errors in y-axis. And here, the internal delay and advanced warning is assumed to be the ones that doesn't trade off with the signaling speed, that doesn't trade off in the hardware speed and accuracy trade-offs. And so here on the right-hand side, we have a system that have a large advanced warning corresponds to the visual feedback system. And then on the left-hand side, we have a system that have a large delay corresponds to the VOR feed-forward system. And if we look at this plot, we will observe a quantitatively different behaviors for the case of delayed system and the case of warned system. In the warned system, what we see is that the rate error will dominate. So the system is optimum with high data rate at the expense of large delay. And this suggests that for one system, having many small axons will lead to optimal performance. On the other hand, on the delayed system, the delay cost will dominate. So the system will be optimum at a low delay and low data rate. And this suggests that in here, having a few large axons will lead to optimal performance. And this is consistent with the observation that the optic nerve has a large number of axons per nerve, and the vestibular nerve are larger in diameter. The axons of the optic nerve and the axons of the vestibular one. And consequently, the optic nerve has greater signaling rate, whereas the vestibular nerve can signal faster. And to verify this one, we can actually do a simple experiment using the audience visual system. And there are two tasks. In the first task, we are just watching a moving object. And this is probably hard for us to see what's written there clearly. And then in the second task, we can move our head at the speed of the first one and look at the static object. In here, you will realize that the task 2 is much easier for us to do than task 1. And this is because task 1 uses the visual feedback loop, and task 2 uses the VOR feed-forward loop. And here the VOR feed-forward loop is much faster than the visual feedback loop. And so here I will use a plot to distill the important design principles we learned from the visual system example. The two axes plot the sum of the rate errors and delay errors in the two loops in the visual system. The diverse case shows when the visual system allows for two loops with diverse hardware. And the uniform case shows when the visual system are only allowed to use hardware that have a uniform speed and accuracy. Both feedback loops is assumed to use the same amount of resources. And so recall from the beginning of the talk that at the hardware level, there is a stringent speed and accuracy trade-offs in nerve signaling. This is due to limitations in biological resources to build and maintain them. And this hardware trade-off will also impose system speed and accuracy trade-offs in terms of the delay and the rate errors for both uniform and diverse cases. But having diverse hardware will have a better system speed and accuracy trade-offs. And then we will name this phenomenon as diversity-enabled sweet spot. And it shows that the effective layered control architectures with appropriate diversity can essentially achieve faster and more accurate performance despite slow or inaccurate hardware. And here we focus on the visual system, but the visual system is not the only place we can observe diversity-enabled sweet spot. And then in the next two slides, I will briefly summarize the other two cases where we can observe diversity sweet spots. So in the first example, we observe that the hardware speed, we get the hardware speed and accuracy trade-offs by assuming that axons will have a homogeneous radius. And of course, that is just an approximation. And here we will relax this assumption and consider axons to have heterogeneous radius. But we will assume that the total resource that can be used by these axons are fixed from the first cases, are same with the first cases. And then we will consider the same control systems and where each type of axons of different radius will have different delay and data rate. And we can similarly show the fundamental limits of the performance. And this is the plot of that performance. And these two axes plots the speed and accuracy trade-offs quantified by the rate error and delay error. And both the diverse case and uniform case have the same resource budget. But the diverse case uses axons of heterogeneous radius, while the uniform case are only allowed to use axons of homogeneous radius. And again, here we observe that the diverse case has much less stringent speed and accuracy trade-offs than the uniform case. And this is another example of diversity sweet spot. And it demonstrates that the diversity within the same layer can boost the speed and accuracy of the control system performance. And then this example gets to the Tobit's comment in the beginning about the fit law study. The previous two cases studies how nerve signaling speed and accuracy will limit the system speed and accuracy trade-offs. And then this study alternatively considered how the speed and accuracy trade-off in muscle acceleration limits the system speed and accuracy trade-offs. And there are similar heterogeneities in muscles, but they require different models to model their speed and accuracy trade-offs. And then this plot shows the speed and accuracy in reaching using a muscle with uniform motor fibers or diverse motor fibers. And in the uniform case, the muscle will contain uniform motor fibers. In the diverse case, the muscle will contain diverse motor fibers. And then here, in the diverse case, the system has better speed and accuracy trade-offs in reaching. And this curve is much more like Fitzgerald curve in the sense that both curves will take the form that looks like a power law or logarithmic, and then the power law-like form allows the system to have a sweet spot at which both speed and accuracy can be attained simultaneously. And so Fitzgerald has been primarily studied from the perspective of information theory. And then these information theory, they are and these cases will be useful when the control part does not become the bottleneck of the reaching behavior. And also in the information theory, the logarithmic form naturally arises from the relation between the information and signal recovery errors. And so from this perspective of just communicating information, logarithmic speed and accuracy trade-offs can be easily achieved without a deliberate design of architecture, layering, or heterogeneity. But from the perspective of control, where the communication is just considered to be one component used in the whole control process, the power laws and the sweet spot from the power laws can only be attained using a deliberate design that can deconstrain the hardware limits. And a naive design can easily lose the sweet spot in the speed and accuracy performance, in the speed and accuracy in system performance. And so this is the Fitzgerald. And so, so next, I will end my talk with the implications of diversity sweet spot and future work. So our result suggests that to create a diversity sweet spot, the system needs to satisfy three conditions. The first is to build an architecture with sufficient layers and appropriate diversity. The second is through practice and learning, the sensorimotor system needs to find out the most appropriate layers to decompose a control task. And the last, it's probably most familiar to all of us, that is to have a good control policy for individual layers. And here, optimizing for point 1 and 2 in blue will intrinsically improve the fundamental limits in system performance imposed from component limits, while optimizing for 3 in green will help realize the fundamental limits or best achievable performance. And despite points 1 and 2 are equally important in achieving robust performance, and the fact that 1 and 2 are complementary to point 3, 1 and 2 have received much less attention than point 3. And this suggests that the points 1 and 2 are important future directions. And in the next slide, I will illustrate the implications of points 1 and 2. So the first point refers to having an appropriate diversity of layers to multiplex subtasks with appropriate speed and accuracy and their diversities. For example, if we consider the visual system example, the visual system has separate layers for object tracking and head motion compensation. And the hardware of the two layers are individually tailored toward the specifics of the control task in each layer. And this allows the two tasks to be multiplexed. However, the capability of multiplexing doesn't come for free. And this is because each layers or adding new layers require additional biological resources to build and maintain them. And given a fixed resource budget, investing more resources in one layer means less resources for the other layer. So one type of resource distribution to enhance the physiology for better performance for certain capability or tasks can potentially sacrifice other tasks. And such trade-offs suggest a waterbed-like effect in the evolution of layered control architectures. And this has been largely overlooked until now. So for example, instead of having the type of diversity of optic and vestibular nerve, we can consider the alternative design. And the alternative design can potentially make us perform better in some other tasks, but worse in the current tasks that we are performing well. And such a holistic perspective of neurophysiology and sensorimotor control and potential alternative design and its implications will allow us to predict what type of task will compete for resources and what will share resources. And understanding these waterbed-like effects can provide new insights into evolution. And so the previous slides talk about having the right layers and hardware, but we still need to learn how to exploit these layers. And this leads to the second point, which states that humans must learn to use appropriate layers. And take the example of this throwing motion of a ball. The beginners will often use central nervous system to control the ball releasing movement. And this will have delays of hundreds of milliseconds. And after enough practice, highly skilled players will learn to use the feet forward control using finger stiffness sensors to control the ball releasing timing. And this loop can achieve a millisecond level resolution. Please, Toby. Sorry, I think you might be muted.
I think Toby's saying that we're out of time.
Oh, okay, sure. This is the last one.
Out of time.
Finish in a minute. And so this millisecond level resolution will help drastically improve the throwing accuracy. And in this example, the sensorimotor learning not only finds controllers for individual layers, but also finds appropriate layers to perform the task. And this type of cross-layer learning will reorganize the use of layers to fundamentally improve the intrinsic limits. And despite its significant impact on the fundamental limits of the performance, cross-layer learning is another underexplored topic. And with that, I will finish my talk with a bunch of examples that demonstrates the diversity-enabled sweet spot in biological system and also engineering system. And here are the potential references and additional reading material.